Hello and welcome to the Fraunhofer IPMS technology webinar. My colleague Fritz Herrmann will talk today about the customized bonded silicon on insulator using CMOS compatible wafer grinder. Fritz is the technical sales manager in the group modules and integration in our MEMS technology department here in Dresden, and is going to give you an introduction to this topic and talks about our experience in BSOI wafer fabrication. If you have questions during the webinar, please type them into the taskbar and we will address these questions after the webinar. The webinar is going to last about 40-45 minutes. And there will also be a follow-up email, including contact information and slides in a couple of days sent out to you. So Fritz, are you ready?
Yes, thank you.
All right, then take it from here.
Thank you very much, Peter. Hello, ladies and gentlemen. I would like to give you an introduction about the capabilities at Fraunhofer IPMS about customized BSOI. We put an addition to the title, which is using CMOS compatible wafer grinder, because this is on the one hand side a core capability that you need to create BSOI wafers. And it's one of the things that is very unique at Fraunhofer IPMS, because having a wafer grinder is not that of a big deal, but having a CMOS compatible wafer grinder is leads in some challenges, and I would like to give you an introduction about these and also what we do in the direction of BSOI developments. Maybe for all of you that are not familiar with the Fraunhofer Society, we are a worldwide operating research institutes collaboration. All our institutes are based in Germany, and we try to develop devices in the different fields of science for the industry, and so is our our title, or what we claim for ourselves, doing applied research for the industry. As you can see, we work in over 80 countries, having representative offices all over the world, in China, mostly in Europe, but also in the US and Africa and South America, where we get in contact with industry partners and research networks to drive the future. When we have a closer look at the Fraunhofer Institutes and how many employees the Fraunhofer Society has, we are talking about 30,000 employees working all over Germany. Within 76 institutes or research units. That means in these different cities that you see here, there are several institutes located, and these institutes have all specific focuses on different topics in the area of research and development. And the total revenue, or the financial volume, that Fraunhofer had in 2021 was 2.9 billion. And this is, some part is done with direct industrial contracts, where we work together close with the industry and industrial partners. Almost 30% is given by federal and state government basic funding, and the rest is expansion investments and defense research, where we also active in. When we focus more on the IPMS side, we are talking about an institute, IPMS, the Institute for Photonic Microsystems. We are talking about a growth over the last years, which we now conclude in a 56 million revenue this year, probably. We're talking about a growth of employees that are working at Fraunhofer's IPMS side of almost 550 persons, where 450 persons are direct employees, such as researchers or administratives or stuff like this. And as you have seen before, Fraunhofer gets money from different sources for the IPMS side. We're talking about almost 50% from industrial contracts, here written in 45%. 80% is given by basic funding and public funding, so projects from the government or the state of Saxony is done with almost 40% doing basic research. Coming to my next slide, where we can see the history of Fraunhofer IPMS. I don't want to go too much into detail, but what I want to point out is that we started in 1992 as a subdivision from the Fraunhofer Institute in Duisburg as an R&D facility, and became independent later on. We got built several facilities, including the CNT, which has right now a very new facility here in Dresden, and also the 200 millimeter side where we do the MEMS fabrication was built in 2007 and got upgraded 2 times in 2015 and 19. And right now we are processing on 200 millimeter wafers, silicon wafers basically. And our latest capabilities that we got into our clean room is a DUV cluster for 130 nanometer lines and spaces, and also the CMOS compatible Wafergrinder that I will highlight in a bit. So what do we do as Fraunhofer IPMS in general? We try to push and pull technologies. What does it mean? We try to create our own research results and pushing these results into devices. Later on, I will have an example how this goes and how we have done it in the past. And on the other hand side, we also try to pull with our customers together technology, meaning that, for example, a startup comes to us and is asking for technology, and we try to develop the technology together with the startup and pushing it into a market application. That's what we mean when we talk about applied research, basically. For IPMS in particular and the clean room there, we're talking about a low volume fabrication. This means that we are not trying to compete with big foundries, but we do quite significantly numbers of devices for our customers. You will get an idea later about this. We also try to help our customers transferring low volumes into high volumes. So what we try to gap is, or which gap we would like to bridge, is that we do a basic understanding of a device and creating this device in a fully integrated device and put it into a process flow, into a major technology that we can hand over to our customer and or to a foundry where it can get rebuilt several million times, which we cannot cover with our facility. So the other parts are not that important. It just shows that we are trying to be on the very forefront of the industry with our infrastructure and the tools that we have, and we try to work as close together with the top leading companies that are available in the MEMS market. What I pointed out is that we have a pull and a push principle that we try to deal with and try to work with our customers together. What does it mean in particular? We have on the one hand side the research and feasibility studies, which can be done in public funded projects. For example, quantum neuromorphic computing is something that we do at the CNT on a very basic level. And we try to mature these technologies and these theories into prototypes and demonstrators. which is basically convertible into TRL level 5 or 6. And then later on, we want to really get into pilot fabrication, sometimes with our customers, that they can use the products and devices in their machines, equipments, or products, so that we cover basically TRL level 3 to TRL level 8 in our 200 millimeter MEMS clean room. The MEMS clean room itself is a R&D and pilot fabrication clean room. What does it mean? So we typically say it's a low volume, high mix approach that we are running it. So we have a lot of technologies, different technologies that are getting done in this clean room with low numbers of each device, of each technology. We are running around 1,000 wafer starts per month, which is basically 12,000 wafers a year. We are operating close to the industry standards in a 24/5, 3-shift operations. That means on weekdays, we are running full-time, and over the weekend, we are still working on long-term processes, but not covered with the operation staff. Right now, almost 100 people are running the clean room, meaning operations and maintenance, but also engineers and researchers around the clean room, working directly in the direction of getting the clean room better and better. We have 2 main lithography tools, 365 nanometer I-line stepper and a 248 nanometer DUV scanner, which I already mentioned in the history and earlier, where we right now are capable to get down to 110 nanometer lines and spaces, which is quite impressive regarding MEMS development, because so far we have not had technologies pushing onto the limits down to 110 nanometers, but right now we see actually applications that are requiring those numbers. We are CMOS compatible, and for the people of you that are familiar with ISO certification, so we are ISO 9001 certificated, meaning that we are trying really to be on the same level as the industry does in the environment of silicon Saxony. So what is the motivation for getting into the BSOI business? Because as some of you probably know, BSOI wafers are you can buy them on the market, but what is the motivation for us to step into this this area? I have with me 2 projects that we are driving or have been driving in the past, where we were relating on BSOI wafers. One is the nanostatic E-drive as a basic principle, where we started at TRL level 3, which was an invention of Fraunhofer IPMS, where we basically have this cantilever here, which has a space between the top electrode and gets divided by a spacer. And when you apply voltage, you get the movement of this cantilever done. And this basic principle was the first thing that we have shown. And later on, we implemented it into a chip level, which you can see here. And the idea was to get a product or an application running where you can push these cantilevers against each other. And what you can do here, you can pressure air, which goes in the direction, for example, here to the right side. And with this pressure, you are able to make noises and sound. And that was the basic idea, where we had our spin-off in 2019 called Arioso Systems. They were doing the first microspeaker on MEMS level, basically, having some pretty good advantages against all the other competitors. And we actually achieved 120 dB this year, or Arioso did, in collaboration with IPMS. And so Arioso showed successfully the use case of this this microspeaker, and actually got acquired in 2022, so in the summer of this year, from Bosch Sensortech. But there we use BSOI wafers, and the question for very specific requirements for this technology popped up in the development phase, and so we decided to have a closer look on the BSOIs, and those requirements were not covered by the industry, so we tried to figure out how can we manage those BSOIs on our own. Another topic is our LiDAR application using microsep scanning mirrors that IPMS is doing over 20 years now. And we had been able to demonstrate with AI, a US company, that we can do a LiDAR system which is super reliable, where you can basically scan and screen the environment around you by the time of flight principle. So you have a laser that gets guided on the mirror. The mirror guides the laser through the entire environment, as you can see here. And then by the time of flight principle, you get an idea what is in front of your car or wherever you guide the laser to. And these mirrors that IPMS provides there are also getting done with BSOI wafers, and also there we had very unique, very specific requirements which we try to achieve with BSOIs that are not commonly on the market. So when we have the motivation that we need BSOIs that are not done at the market, we figured out if there's an opportunity to create BSOIs on our own, and we checked our capabilities and what Fraunhofer IPMS in this 200mm clean room does is on the one hand side the surface micromachining to create 2.5 or 3D structures by a sacrificial layer technology. But this is not what we can use here, or where we can use capabilities from this side, but from the bulk micromachining on the bottom left here, we can use actually a lot of core capabilities to create BSOIs. So for example, when we go to the next slide, there's just an explanation what bulk micromachining means. You basically etch structures deeply into substrate or bulk, so-called, and this contains a lot of things around, and these things that are needed for the bulk micromachining are exactly these ones. So trench filling for isolation. Once you have those these trenches etched, you have to sometimes refill them. You need a PVD tools to get metals on top of, for example, these mirrors. And what is right now leading into my topic is the grinding for the thinning. So often you etch deep into the bulk, and later on you thin the substrate. And thinning is one thing that is really important for BSOI wafers. Also, when we talk about wafer bonding, which is also commonly used in bulk micromachining, this is something obviously coming from the title of BSOI, so bonded silicon on insulator substrates. This is another capability, and typically typically bulk micromachine devices are using already BSOI substrates. So you need a good understanding of how to handle it, how to work with these materials, and all these capabilities together leads us into the idea that we could do BSOI wafers on our own using the Wafergrinder. And the idea was to get this Wafergrinder for wafer thinning, okay, but for BSOI preparation to get our own BSOIs. And what we need to make sure is that these wafers that are getting grinded are CMOS compatible, because, as I said, our clean room contains CMOS compatible materials and tools, and so that was a big requirement for the tool, which we got installed 1.5 years ago in our clean room. So what are the key aspects of this grinder? We have basically 4 stages. I have on the next slide an overview about the different stages, where we can grind down on 2 stages, get a CMP done afterwards, and getting measurements and cleaning done on the final step to see if there is another iteration necessary or not. And what we can do is very flat surfaces with the included CMP module. Here on the right hand side you see the ranges that we achieve with the roughnesses of the top surfaces on silicon. When we have a look into the tool, so typically a grinder can have 2 or 4 stages. So when you have 4 stages, you get the wafer inside the tool. It runs in a circle basically on 4 different grinding wheels, and each wheel has its own purpose. So as I said, the first 2 wheels are polishing the wafer basically down with huge heights that you get rid of the wafer. So talking about several microns. And later on you CMP the final step, because you get those called grinding suns, which is a very unique optical thing that you get when you grind with those wheels. And later on you get rid of them with the CMP wheel, and later on we have a cleaning module which makes sure that we get rid of all particles that are got introduced into the wafer within the process. We are very aware of the contamination of our tool, because the CMOS compatibility is very important for us, since we also have ASICs running in our clean room. And so we want to really make sure that our tools are clean. And here you can see only as an introduction that we monitor our wafers running through the grinder, and here you can see that we are always in the specifications for the CMOS compatibility. What we also needed for this project, and also bought within the investment round where we got the grinder, was a infrared reflectometry and spectroscopy module, where we can detect the thicknesses of the layers that we want to grind down. And this we will later see is very important for us, getting the right thicknesses of the wafer done for the BSOIs. But this was only for a brief overview. How actually did we do the BSOI in the recent year? So our goal was to get several wafer thicknesses done. Later on, we also wanted to integrate cavities and buried metallization on the BSOIs, and we also thought about doing several dopings of wafers as either handle or device layer or device wafer. And what is important and what is critical in those kind of processings, I will show you now. So what were the goals? We wanted to basically bond 2 wafers, and our goal was to do a BSOI substrate in this run with 75 microns, 1 micron of oxide and 400 microns of silicon again, and the other one was 7.5 microns, 1 micron of oxide and 650 microns of silicon. So the basic idea is that you on the first hand side get an oxide onto the handle wafer applied with a wet edged oxide, not wet edged, wet applied oxide. You then pre-bond these wafers. So that's a very basic idea of the process flow. I will go into the details on the following pages, but to get an idea, you pre-bond those wafers, then you get them together, an oxidation to get them put together as a lasting bond. Then we did the edge trimming to get rid of the edge and don't have any issues with the edge of the wafers. Get rid of the silicon that lasts on the edge by xenon difluoride etching, and later on we get rid on the top side of the oxide and grind back to the target of the device wafer. So this is the basic idea that we had in mind. This was the project idea. And what we did first of all was measuring the thickness of the handle wafers, preparing the handle wafers, and getting the thickness done for the handle wafers, because you have to make sure that you know from each wafer, each value. As you can see, there are deviations in the thickness of the wafers all over the board, and when you grind back to a target thickness, you need to make sure that you only grind as much as the difference of the given number and your target number is. So what we can see is there's always an outlier here for our processing. Here is wafer 10 and here's wafer 1. And for the thin handle wafers, we have a deviation which is not that critical as we see at the thick handle wafers. But yeah, this will become a challenge later on in the processing, as you will see. What we also measured was the thickness of the device wafer. So this is what I basically mean. We started with monitoring wafers, which are typically 720 to 725 microns thick. And here we need the idea how thick they are in particular, because we needed to go down to 7.5 microns, and you only can get down to these values if you know the exact number of the wafers that you have up front. Then we applied, as I said, the oxide on the handle wafers. Here you can see the values that we applied. Here on the right side, you see we almost were in the specification of 1 micron plus minus 1%. So that's pretty much what we tried to achieve here. And this was a trial to get down to 500 nanometers thickness of the oxide. Later on, when we try to bond those wafers together, we actually have a pre-bond process which works with pressure. So you pressure those wafers together, that they have a basic bonding done, which is not sufficient for processing, but getting them later on into the furnace to get an oxidation done to bond them basically together. It is sufficient, and then we get really the entire bonding of those two wafers, which you cannot get, break or open up again. And what you see here on the right side is an IR measurement or an IR camera shining through the wafer to see whether there are air bubbles or particles bonded in. And as you can see here, there are basically no residuals, particles, or anything that interferes the bonding of those wafers. Now there's a process step which we thought is a pretty common one and which is quite easy one, but we actually faced the fact within the project that this is very critical aspect also for later stage processing of those wafers, and this is the edge trimming. So what we basically did, we diced the top wafer in the profile that you can see here on the top, and dice it back from the edge of the wafer to the middle of the wafer with different steps. And you can see here the values that we tried to achieve. And they are the homogeneity is not good enough in our from our perspective, and so we try to get some iterations done to improve the spread of the edge trimming. So we wanted to achieve actually 15 microns, and what we get here, you can see there were only 1 or 2 wafers that managed this, and sometimes we came up with 40 and more, and then we iterated again, and then we see that we are almost at the 15 microns thickness of the trimmed edge. Then we try to achieve the handle, the device layer thickness, and as I said, you grind down the bonded wafer from the top side down to 7.5 ideally, but what we did here, you can see we ended up in much lower values than we wanted to achieve, and this is the reason because we did not take in consideration that close the thickness of the device wafers. So we were kind of so we had the values, but we didn't take this in consideration when we started the grinding process actually, and then we got some wafers left for this processing, and we tried then to not get 7.5 but 5.5 as an iteration, and on the second run, on the second lots and the second wafer run, we actually achieved this by taking in consideration the thickness of the device wafer and the device layer. Also for the 75, it took us a while to manage this process quite well. As you can see, a wider spread than we would usually try to have. And then after another iteration, we managed to get down to almost 75 over the entire wafer, which was an improvement, but was harder than expected, actually, to be honest with you. So I want to conclude what we did here was showing that we were able to do BSOI wafers with different handle wafer thicknesses, with different oxide layer thicknesses and different device layer thicknesses. We showed that we are capable to do it with our CMOS compatible grinder, and right now we are doing customized BSOIs. So these values are values that we had been discovering when we planned the project for some internal projects, but once there are customers and asking for customization of thicknesses, for example, then we are capable to do this right now. And right now we are able to push new ideas of MEMS developments and MEMS devices with these type of self-made BSOIs. What's next in this project, and with the results that we got within this project, is doing multi-wafer stacks. So not only 2 silicon wafers bonded together, but actually 3 or 4, also divided by oxide, for example. We want to process not only the 1.5 millimeter thick stacks that we had so far, but we also want to increase the thickness of the stacks up to 3 microns and also down to 300 microns, because maybe if you remember, we were talking about stack thicknesses of almost 400 and a bit. And right now we try to go down to 300 as well, but that's not very high rated in the priority list. What we actually did is cavities on SOI to get pre-processed cavities into the SOIs and everything that comes along with that, because this is something that we see becomes more and more important for MEMS fabrication. What we also do with our grinder, or what we try to do next year, is getting TSV structures done with grinding processes, that you basically get rid of the backside and having open trenches through the entire wafer. And what we tried to do, but actually we didn't in the recent project, was working with different dopings. The reason why is that we had not access to doping materials, but meaning that we don't have any machines that can dope the wafers. Basically, we could have used different doped wafers as basic material, but that's what we did not highlight yet, and that's not what we had been asked for the recent years. But this is something that comes first around the corner when you think of what could be done next when you are capable to do standard BSOI wafers, is that you change the doping of the wafers regarding the requirements of the customer. Yeah, and that's basically what I wanted to show you in this webinar. I hope you took something from it, and I'm happy to hear any questions from you.
All right. Thank you, Fritz. Thanks a lot for your presentation. Until now, I can't see any questions. So if you have any questions, please type them in right now in the taskbar. I will address these questions to Fritz. Or maybe your presentation was clear enough. In the meantime, maybe I have a question. Maybe we can go into more detail regarding the outlook. So what are the next steps regarding the development of BSOI at IPMS in terms of what are the essentials, what needs to be done in any case, and what is maybe nice to have? So maybe you can talk about that for a couple of minutes or a couple of seconds. Sorry.
Sure. So for us was important actually to try different dopings, but we got rid of it because there were no more requests in this direction. But what we faced the last 1.5 years was that predetermined structures, meaning cavities or metallization or stuff like this on SOI wafers, are becoming more and more interesting for customers, and also features that you can implement with the capabilities that IPMS has. So etching capabilities, for example, you can bring additional features into the SOIs that are not implemented right now by any company. So I can tell you not too many details, but we have a patent running in the direction of getting more security into technologies running with SOI wafers with predetermined structures on the SOI wafers to make your devices later on in the field more safe. And this patent is actually released, or it's at the patent facility, and will be released early next year. So this is where we try to get our next steps into getting security as a feature into the SOIs.
All right, thank you. Interesting. That's the good news. So in the meantime, I got a question, or two questions. First one is, what is the post-CMP thickness uniformity of the device layer?
So we actually had the number given by the the supplier of the tool. So we actually achieve 1 to 2% total thickness variation of the device layer and also the handle wafer. But this is what we also achieved meeting the specification of the tool. I hope this answers the question.
Okay. And the second question from the same person is, what is the minimum thickness of device layer we can produce by BSOI process?
So actually there are not that many limits. We are right now also thinking of going down to 500 nanometers, but this is obviously very challenging, but there are no limitations. The only thing is that you have to take considerations how to go ahead with these thin structures. And but from the device layer side, there are basically no limitations how far you can go down when you were quite accurate. Your first question was obviously about the thickness variation. So when you talk about 1 to 2%, and this is also very significant. As lower you can get, the more influence these variations will later on have for, let's say, a membrane or something like this. But I have not seen smaller device layers yet down to 500 nanometers, but I don't see any blocking point there.
All right. Okay. He says thank you, and that I guess that answers his questions. And there are no more questions as I can see. And then I think we're done for today. Fritz, thank you again for your time, for your presentation, and also the audience for taking part in our technology webinar. This was the last webinar for this year. As I said in the beginning, there will be a follow-up email with the Fritz contact information. If you have questions in the future, you can just write them directly. And with that, we will say thanks again and have a nice Christmas time, and take care, and probably see you next year, hopefully.
Bye-bye. Thank you for your
Bye-bye.
time.